Hi everyone, welcome to the 31st session of the Porous Media Tea Time Talks. I'm Catherine Spurin from Stanford, and I'm joined here today by my colleagues Singh from Heriot-Watt, Federico Lanza from Université Paris-Saclay, sorry for my pronunciations, and NTNU, and Sarah Perez from UPPA. We have two really interesting talks today, which I think will span like a good range of porous media research. So our first speaker today, without hesitation, is Tinhinane from UPPA. She has an engineering degree in hydraulics and a master's degree in geomechanics structures, and she is currently a second-year PhD student studying X-ray tomography for the in situ characterization of crystallization damage in lead artworks. So I will hand the floor over to you now.
Thank you for, hello everyone, thank you for giving me this chance to present my work for you. Without hesitation, I will start with my presentation. So salt crystallization damage is one of many mechanisms that threatens our cultural heritage. So most often artworks are multi-layered structures, but we can find with mono-layer structures. So they have different physical properties. In recent years, much have been done to understand the salt crystallization process in one-layered materials, and not really much has been done on studying the layered materials. So here with my project, we are aiming to study the damage caused by crystallization in layered materials. So wall tiles are an art mark that distinguish many European cities. So unfortunately, it is highly affected by salt crystallization damage. So for our project, we have chosen to work with these Dutch tiles. So usually these wall Dutch tiles are multi-layered materials. So they are composed of a clay body, which is a fired mixture of clays. We have this glaze layer, which is like a glossy painting on top. And most of the times we have artistic paintings as well. So the damage that occurs in these tiles are mostly represented by these three damages. So we have shivering, which is the removal of the glaze layer with a part of the clay body. We have peeling, which is a clean removal of the glaze. So these two damages are caused by salt crystallization. But sometimes we have this damage, which is crazing, which is these cracks, little cracks on top of the glaze, which is caused by manufacturing defect. So it was bad manufacturing, which causes this kind of damage. So in order to investigate the salt crystallization process, we have to be able to reproduce this process in the laboratory. So which means that we have to put salt weathering protocol that allows us to mimic the real salt weathering. So a reliable salt weathering test is described in the literature as we can see in this illustration. So we have two stages. So we have an accumulation stage in which we have salt accumulating in our porous media. And then we have a propagation stage in which the damage is starting to appear in the porous media. So the most common case that we can find is when a building that is composed of porous materials is exposed to capillary rise. So the groundwater, as we know, is composed of many minerals. and it may contain salts. So when this minerals is capillary uptaken by the porous medium, and with the evaporation, we will have some salt crystals that are appearing in the pores, and with the accumulation of this salt, we will have damage. So for my test, I have been using these Dutch tiles that actually they come from a company in the Netherlands. So they are real tiles that were once on a building, and they remove them and they sell them for reuse. So these tiles are composed of 2 layers. So we have a glaze layer and we have the clay body. So the clay body is like calcium-rich clay, and the glaze is composed of like really heavy materials like tin and lead. So the X-ray imaging of these 2 layers can give these 2 images. So as we can see that the glaze is have these big pores that are disconnected, but actually they are caused by the manufacturing process. It's just air that was trapped in the glaze. And we have the clay body that is appearing very heterogeneous. So in order to investigate if whether or not there is already existing salt in the structure of these tiles before doing any tests with them, so we have conducted an X-ray diffraction analysis in which we have concluded that indeed there was no presence of salt crystals. And then porosity investigation was conducted on the clay body of the intact samples, as well as on the clay body of crazed samples. So the results showed that the clay body of the intact samples showed more porosity than the clay body of the crazed samples. So when we have higher porosity, we will have higher chance to have more salt accumulating in our structure. So we have conducted the preliminary weathering test. So as an accumulation stage, so we took a core in our tiles and we have contaminated it with 1.26 mole of sodium sulfate. And then after the contamination, we have dried it in a climatic chamber in this 25% relative humidity and 21 degrees Celsius. So we have done this for 3 cycles, contamination, then drying. And before each cycle, we conduct a scan in order to compare the state of the sample before each cycle. Also, we weighted the samples so we could easily see that there is salt accumulating inside, in which we have a bit more for the crazed samples. So this is an example of the scans that we have conducted. So here we have a scan for the initial state of the sample, so before the contamination with the salt. So this picture represents this region, which is in the interface between the glaze and the clay body. And this one here represents the clay body. And this second picture is representing the same region after 3 cycles of contamination and drying. And this one as well is the same with after 3 cycles. So when we look at these 2 images, we cannot see any changes really. But when we do image treatment, we can do like a subtraction, and the subtracted image, we can see that there is actually salt accumulating inside of the structure, and this is represented as like a block, as clusters of salt, and this is only observed in this upper region, in the interface between the glaze and the clay body. So using also the image treatment, we can look at the evolution of the porosity. So here in blue, we have the porosity of the initial structure before the contamination. And then in red, we have the porosity after the 3 cycles. So we can see that clearly that in the upper region, we have that decreasing in porosity, which means that there is indeed salt accumulating inside of the structure. So after this accumulation stage, we'll have the propagation stage, where we will have the damage. So in this one, we have conducted one cycle, but this time we dried it for 24 hours in ambient conditions with 42% relative humidity and 21 degrees Celsius, and then transfer it to the climatic chambers, the climatic chamber, and dried it in the previous conditions. So here again, we have monitored the accumulation of salt by weight, in which we see that there is accumulation. And also, we have conducted another scan. So at first glance, visually, we saw that the sample was cracked. So in the X-ray, we can see that the interesting thing is that the crack is really following the pattern of the salt cluster. So the damage only happened where in the interface between the salt cluster and the other part of the clay body. And also with the monitoring the evolution of porosity, we can see that there is salt clusters everywhere. And here we have an increase in porosity, which is translating to the crack, the big crack that we have. So to conclude is that this salt weathering that we have conducted actually mimics realistic scenarios of salt weathering that really happened. So for example, here in the literature, we have these damaged tiles, which are real damaged, and with comparing it to our images of the damage that we got from the weathering protocol, we can see that it is like in a similar pattern. So thank you for your attention, and I'm ready for your questions.
Okay, thank you, Tinhinane. I don't know if there are questions from the chat. I would start, if there are other questions, urgent questions, I would like to ask you if you have analyzed or you are considering analyzing actually how the salt, in this case, the sodium sulfate, aggregates and crystallizes, because you're talking about crystallization. So I'm expecting some sort of regular bonds, at least some sort of lattice, like a proper crystal. So what does it mean exactly, crystallization? Or is in general an amorphous solid that solidifies with randomic bonds?
Thank you for the question. Actually, in this study, we are more interested in the damage that is caused by the crystallization of the sodium sulfate. And with the technique that I'm using, which is X-ray tomography, we cannot really see the crystal because you should have really high resolution to be able to see the crystal. So we are in a just like interested in how this damage, but in the mesoscale, like in the
Okay.
yeah.
No, sure. Because I just expect that, for example, if the sodium sulfate crystallize with a regular lattice with a proper crystal, maybe the properties of this damage can be different because the crystal is harder to be removed. For example, the bonds are stronger in general rather than an amorphous solid. So maybe putting attention on that can be useful. I don't know. I'm just guessing.
Yeah. I usually hear like the crystals that are damaging is mirabilite and tannardite, like the transmission from tannardite to mirabilite. This is what causes the damage.
Okay.
Yeah.
And have you considered other kind, or are you going to consider other kind of salt rather than sodium sulfate? I
Yes.
suppose that it is common, of course, in cultural heritage, but I don't know if you have considered other kind of salts.
Yes, actually, we are working also with sodium chloride, but for now we didn't get any damage with the use of this salt. So we are considering other protocols maybe to get damage with this salt.
Okay. Really interesting. Okay. Thank you.
I have a quick question. This is just a curiosity or general question. So in your experiments, you did 4 cycles and then you stop when you see the crack. Do you have any plans to go further? Like if you do further cycles, even if it cracks, or you think it doesn't matter then afterwards?
Actually, we didn't think of doing more cycles after the cracking, and again, this is still like a first weathering protocol and development. Yeah.
Yeah, sure. And I'm assuming, let's say if we got stones, building stones, and some of them under some load, so you have some compression already on that would affect, because in your experiments you don't have any load on these ones, right?
Yes.
Would it? But I think you show that the laboratory ones which you see, they're very comparable to the field scale what you see, right, already there.
Yeah. Actually, yeah, it should affect it because the tensile strength will be changed. So yeah, with some load, maybe it will be easier to damage the structure. Yeah.
Okay, thank you.
Thank you.
Okay. Then if there are no other questions.
And there's one in the comments.
Oh, okay. How can I see? Okay, thank you. Okay, so I'm going to read it. Hi there. I noticed that you reduced the relative humidity for inducing crystallization rather than increasing temperature. What's the motivation for this choice? And how do you control the airflow rate?
So actually, like the damaging process with sodium sulfate is when you go from this phase from tannardite to mirabilite, or from mirabilite to tannardite. So mirabilite in the climatic conditions that I have used before in the accumulation stage, I only will have tannardite. So the use of this in the 4th cycle in this conditions, ambient conditions, is to create this mirabilite phase. And for the airflow, actually, I'm using a climatic chamber, so it's there is no airflow. So it's standard. You can specify the climatic conditions that you want, and you will have these conditions inside.
Okay. Are there any other questions?
I have just a quick question, if that's okay. I think it was maybe slide 16 or 17. I'm not sure if it's easy for you to go back. Maybe 17, I think. Yeah, this one. So, I mean, this looks really interesting, but it seems like the areas that are with the higher porosity look like the most affected. I'm not sure if I'm looking at this right, but is there a way that you're going to change how these tiles are made so that you can kind of minimize the amount of salt weathering, dependent on the pore size of the within the tile?
Yeah, I mean, if you control the manufacturing process, you will have nicer tiles that were not affected by this salt weathering. But the problem is that when the tile is aging, there are some defects that are created inside. So even if you minimize the porosity at first, but with the aging, the tile will be vulnerable. So it will become prone to the salt damage.
Okay. So if there are no other questions, I would like to thank you again, Tinhinane, for your really interesting presentation. And I would like to present our next guest, which is Weiyu Li. So welcome, Weiyu Li. Weiyu Li is a PhD candidate in the Department of Energy Resources Engineering at Stanford University. Her research focuses on the modeling of lithium ion or lithium metal batteries, for example, effective model of ionic transport, simulation of dendrite growth, and other relative features. So, Weiyu Li, it's your turn.
Thank you, Federico, for the introduction. Today, I would like to present my work on the modeling of lithium dendrite growth in lithium metal batteries. Each battery cell consists of two electrodes, the cathode and the anode, and they are separated by a separator and the electrolyte that would enable the movement of ions inside the electrolyte. And in the lithium-ion batteries, people use graphite as the anode material, while in the lithium metal battery, people would use lithium metal as the anode material. Because lithium is the lightest metal with the lowest electrochemical reduction potential, and it has a much higher specific capacity, like 10 times greater than that of the graphite-based anode.
So Weiyu, to interrupt, but could you go onto the full screen for your slides?
Oh, yes. Okay, sorry, I share a wrong screen.
Oh, no worries.
Okay, I will restart. I think now is the right one. Is it coming up?
It just has a loading symbol at the moment.
Yeah.
Maybe try connecting and disconnecting the screen share.
Okay, now I think I got it. Try this.
Yeah, that looks fantastic. Great.
Okay, now it's full screen. I'm sorry. So I would continue on where I stopped. Is that okay?
Sure.
Yeah, that's fine.
Yes, okay. So I just talk about why we use lithium metal as the anode material, because it has a higher specific capacity than the graphite-based anode material. And so using the rechargeable lithium metal battery is one of the most promising electrochemical energy conversion and storage system to meet the power and energy demand for electric vehicles. However, there is a severe issue related to lithium metal battery. That is, during the charging process, the lithium metal would deposit on the anode and form the lithium dendrite, which would cause a rapid capacity degradation. And when the lithium ions concentrate around the dendrite tip and would form the spiky structure to cause the short circuit. And the formation of the lithium dendrite is one of the major issues that impede the commercialization of rechargeable lithium metal batteries. How do people control the lithium dendrite formation? Like they would use like concentrated electrolyte, pulse plating or flowing cell, and mitigating side reactions and enhancing the solid electrolyte interface or applying an external pressure. However, the underlying mechanism of dendrite formation and continued propagation is not fully understood. So here we conduct a linear stability analysis of electrodeposition on the lithium anode in lithium metal batteries. And we would investigate the balance between the stabilizing effect and the destabilizing effect. And we would solve for the dispersion relation and look at the system parameters. And we also focus on the effects of preferential diffusion with electric field dependent transport coefficients. And next, I would give a short overview of the literature. And there are like several recent advances in morphological stability analysis of electrodeposition. And people study the linear stability of transient electrodeposition and the steady electrodeposition, while assuming microscopic electroneutrality or accounting for the extended space charge density. So the problems I'm solving here is first to relax the assumption of electroneutrality, and also we would apply electric field altered electrolyte diffusivity, and we will consider the anisotropic diffusivity. And next, I would discuss the methods and the problem formulation. And here we consider a two-dimensional half-cell domain to study the electrodeposition on the lithium anode. The lithium metal electrode surface initially locates at x equal to 0 and is in contact with the electrolyte. And the lithium ions in the electrolyte would transport from the electrolyte to the lithium metal surface and undergo Faradic reactions and the electrons and with the electrons at the electrode surface. And then the lithium ions would reduce to the lithium atoms and then deposit on the lithium metal surface. And for to describe the transport phenomena, and we use the Nernst-Planck equation and the Poisson equation for the electric potential. And for the boundary condition, first the anion is inert and does not react with the electrons at the lithium metal surface. So the flux is 0 at the surface for the anion. And for the cation, there is a reaction rate, which would be given by the Butler-Volmer equation that I'm going to show later. And at the boundary, the right boundary is the electrolyte, and we apply the Dirichlet boundary condition with 0 electric potential and fixing the concentration of cations and anions. And we also apply a minimum cation concentration at the lithium metal surface. And also, along the y dimension, we apply a non-flux boundary condition. And here, R is the production rate of lithium metal I just mentioned, and given by the Butler-Volmer equation. And eta is the activation over potential, like by taking the difference between the applied electric potential and the electric potential in the electrolyte and the standard electric potential. And the time evolution of the H is the surface height of the electrode is given by the current into the anode. And also here, we consider the effect of electric field altered diffusion coefficients in the electrolyte. And here we introduce the electric field dependent diffusion coefficients. And here we could see with the presence of electric field, the diffusion coefficients of cation and anion would be altered, and they would be direction dependent. And then we studied the stability of electrodeposition on the anode along the x direction by applying a sinusoidal perturbation in the y direction. By applying perturbation at the surface height, we can also get perturbation in the electrical potential and the concentration. And then we would do the Taylor expansion around the base state interface x equal to 0. And we can also evaluate the reaction rate and expand into first order. And then we can do the same thing, like expanding the diffusion coefficient, like to first order. And then after substituting these equations and the expression for the diffusion coefficients into those governing equations, and then we can collect the order 1 and the order epsilon term, and we can obtain the equations for the base state. And here are the equations for the base states and the boundary condition for the base states. They are just the steady state equations for the PNP equations. And they, here are the equations for perturbed states and the boundary conditions for the perturbed states. And to solve this system of equations numerically, we use to solve the base state equations, we use the MATLAB boundary value solver function, and then we solve for the perturbed state equations, and we follow this numerical method using 1D second order accurate finite difference approximation for uniform grid with endpoints. And then we can solve the resulting generalized eigenvalue problem with MATLAB's eigenvalue function solver. And then we can see some results. And the first, this figure shows the base state cation concentration and anion concentration and the electric potential and the charge density by using the constant diffusion coefficient. And we could see that under a small applied electric potential that the cations are not depleted at the electrode surface. And from the charge density plot, we could see that a local electron neutrality holds even close to the electrode surface. However, under a large applied potential, that the base state current density would exceed the limiting current density, the cation concentration is close to 0 near the electrode surface. And we can see from the last plot that there is an extended space charge region, like extends to 0.02 L. It's a large space charge region. And we can also observe a very high electric potential gradient near the electrode surface when applying a high electric potential. And next, we would investigate the effect of electric field on the ion diffusion and the electrodeposition. And first, we compare the charge density distribution at the base states using constant diffusion coefficients and electric field dependent diffusion coefficients. And here we could see under a small applied potential that electroneutrality holds for constant D and electric field altered D, and their results agree. However, under a much higher applied electric potential, we can see that a local electroneutrality is violated, and there is a difference. We can see from the zoom-in figure that there is a higher charge density for the electric field altered diffusion coefficient than using the constant diffusion coefficient. And finally, here I show the numerically computed growth rate that is plotted against the wave number using constant diffusion coefficient and the electric field dependent diffusion coefficient. And therefore, several applied electric potential. And here we can see using a low electric potential that the growth rate is 0 for range of wave number, which means the electrode surface is unconditionally stable. However, with increasing the applied electric potential, we could see within a range of a wave number that the growth rate becomes positive and reaches a maximum growth rate at a maximum wave number. And then further increment of the wave number would decrease the growth rate, and finally the growth rate would go down to 0, and which is the at a critical wave number, and becomes negative with increasing wave number, which means the electrode surface is stabilized. And also, we can see that by using the electric field altered diffusion coefficient would give us a higher prediction of the growth rate, like by 20% in this case compared to the using the constant diffusion coefficient. So in summary, there are several bullet points. And first, the electrode surface is unconditionally stable under small applied potential, and the local electroneutrality holds under small applied potential while there is a extended space charge region under high applied potential. And we also conclude that under high applied potential, using electric field dependent diffusion coefficient, the maximum growth rate is higher than the maximum growth rate by using the constant diffusion coefficient. Yeah, thank you. I'm happy to take any questions.
Thank you for this great presentation. It was quite a new field for me. I learned quite a lot of things. Thank you once again for this beautiful presentation. If from the studio, if anybody has questions, please you can ask. And to the audience, if you have any questions, you can type into the chat window. I have one bit curiosity-driven question, maybe just very naive. This is actually nice. I think the last slide summed it up using constant diffusion coefficient or not. I was curious, although maybe it's not practical. If you change the temperature conditions and stuff like this, how would that impact the dendritic growth?
Oh yeah, thank you for the question. Like temperature is a very important factor in modeling dendrite growth too. But here we use a constant temperature. Like for example, using changing the temperature and the diffusion coefficient would be dependent on temperature too. And another interesting thing is like in the follow-up work, we would also include energy equation and to include the impact of temperature. That would be interesting.
Yeah, thank you. Yeah, I think it will be very nice to see where we do see the optimum solution so that we can control this dendritic growth, right? So that you don't have short circuits. Yeah. Thank you so much. Anybody else has questions?
I had a question as well, if that's okay.
Yeah, sure, absolutely. Please go for it.
You were saying like the different diffusion rates had like a really large impact on like the amount of growth. I think that was on your final slide. But I was just wondering like what the impact that would have like in the batteries. Sorry, I'm a bit new to the research, but like is this like a good thing or like a bad thing?
You mean like changing the diffusion coefficient in the electrolyte?
Yeah.
Oh yeah, so for the battery design, it's a very important factor to consider, like what kind of electrolyte we want to consider and what are the like the behavior of the ions in the electrolyte, right? Like when the ions transport to the electrode, and we want to find like electrolyte that would give us like would surprise the dendrite growth, like we do something about the electrolyte, whether altering the diffusion coefficient, for example, or by applying an electric field externally, and that would optimize our battery performance, like by mitigating those dendrite formation.
Thank you. Another one short question is that so you're doing this simulated work. So you have any experimental data stuff onto compare against the results?
Oh yeah, this is another follow-up work. We want to also like collaborate with people who do the experiments, but I don't know about experiments.
No worries.
So we want to also like to see if our results using like for example the electric field dependent diffusion coefficient and would agree like better than the previous one than using the constant diffusion coefficient.
Yeah.
And also we also want to explore like the state of the art like solid state battery using the solid electrolyte and like by applying our analysis and then compare to the experimental results.
Fantastic. Cool.
Thank you.
And okay, I don't have a question from the audience, but there's a comment from Wow Wong, Yao Wong, for he thanking for the nice, impressive talk, which I totally agree to. And if there's no further questions, I'd like to thank you for this fantastic presentation once again. And I would like to thank both of our speakers for today's presentation. There was a nice discussion, and Sarah is back with us, and it's time to wrap up the session. So I would like to announce our next speakers. We got two fantastic talks coming up in 2 weeks. The first one is from Kundani Bha Mitra, who's going to talk about hysteresis and dynamics of flow in porous media. And the second one is from Stefan Lunova, who's going to look into contact angle dynamics during miscible fluid flow at the pore scale. So please join us for the next session and we can discuss. And for now, thank you for watching our studio. And if you have any questions, and you can contact us on porosmediattt@gmail.com. Not only questions, if you have comments. And this is our beautiful team growing. And with this, I'd like to close the session and see you in 2 weeks. Thank you. Thank you, everyone.